All right. We are going to skip ahead a little bit in section 4.5. I'm going to save the middle piece to do when I get back because I think that'll be a little bit easier for us. So let me share the notes here. Okay, so this is where we left off. We did example 3. We're actually going to skip the rational root theorem for now, and we're going to skip ahead to where it says solutions and the graph of a polynomial. I think that this will be a little bit easier to figure out since I'm not going to be there. So hopefully that helps you out some, okay? So we've already seen what some of the solutions look like, and we saw an example that we did yesterday where we got a factor that was squared. So that meant that even though we got, I don't remember what it was, maybe -3, we got that twice for a solution. We only have to write it once because it doesn't make sense to say, you know, I have -3 and -3 as my solutions. So we only have to write it once. Those roots that come from a factor that's squared or maybe cubed or even a higher power, those are called a repeated root. So the roots of an equation are another word for the solutions. You're going to hear me say solutions and roots at the same time. So the number of times that a factor appears is called the multiplicity of a factor. So let's say that I have a polynomial equation that's factored to, say, 2x squared times x minus 1 times x plus 7 to the third equals 0, okay? We would set all 3 of those factors equal to 0. Whoops, I'm scribbling. And when we do that, I would get multiple solutions. I would get a solution from this x right here, so x is equal to 0. I'd get one from this here, x equals 1. And from right here, I'd get x equals -7, okay? So those are the zeros, and each of those came from a different factor. To find the multiplicity of each of those roots, we look at the factor that they came from, and we look at the exponent. So this 0 came from an x squared term, so that 0 solution has a multiplicity of 2. X minus 1, that doesn't have an exponent, that means it's to the first power, so the solution x equals 1 has a multiplicity of 1. And then -7 comes from a factor that has a degree of 3, so that means the multiplicity of -7 is 3. So you're going to get your different solutions, and in order to determine what their multiplicity is, you have to back up and look at the factors that they came from. But it's real easy to figure out because all you're looking for is the exponents. So what's really interesting, and this is why I said that we really want to practice writing our factors using exponents if they repeat, because that multiplicity tells us a lot about what the graph does. If you remember before Christmas break or winter break, we graphed polynomials, and you just had to plug in all the points to a table and kind of estimate what it was going to do. Well, if we can get it in its factored form, sorry, the camera's moving around. If we can get it in its factored form, then that multiplicity tells us what the graph is going to do at each of those points. So the 2 things we want to watch for is the multiplicity even or is the multiplicity odd? So if the multiplicity is an odd power, so the first power, a multiplicity of 3, a multiplicity of 5, and so on, then the graph is going to cross the x-axis at that root or that x-intercept. So for example, if I had an x-intercept right here with an odd multiplicity, the graph is going to do whatever, but I know that it's going to cross at that point. And it doesn't have to go straight. It could kind of squiggle through the x-axis. We don't know what it's going to do, but it's going to cross. If it has an even power, then it's going to just touch the x-axis and then turn back around. So any even exponent, let's say that I had this here, my graph is going to come up and then turn back around. So it doesn't actually go through the x-axis. It touches it. So we do have an x-intercept there, but as soon as it touches it, it changes its mind. and it could do that from the top either. And so that's why I always call that a bounce on the graph, because it just bounces off the x-axis rather than actually crossing through it, okay? So then the other thing that we can kind of keep in mind is the bigger the multiplicity gets, the flatter the graph gets at that root. So for example, if we think about, let's say it's an odd multiplicity, if my 0 is right here, a multiplicity of 1 might cross through kind of like a line, just a straight cut. A multiplicity of 3 is going to kind of flatten out over here. A multiplicity of, say, 11 is going to get even more flat at that 0. So every time the multiplicity gets bigger, the graph basically starts to slow down before it gets to the x-axis, and then it goes slowly on the other side before it starts to speed back up. So that's just kind of a side note so you can anticipate what the graphs are going to look like. All right, so how do we put this all together then to get some information about the graphs? So using this information along with what we know about end behavior, and I'll refresh your memory on that, we can get a reasonable estimate of what the graph is going to look like. These are just going to be sketches. We're not going to worry too much about how high the graph actually gets or whatever. We'd have to use a table to figure that out. But this information will give us enough about the shape of the graph that we can kind of decide, where does it go up, come down, where does it bounce and cross, and we can get a decent picture that way. So end behavior, let's just remember how to do that. So to find the end behavior of a function, we need to look at the leading coefficient and the degree of the function. Okay, so the leading coefficient might be 2 and the degree might be 5. And when we looked at this before, I think the easiest way to do this is to kind of set up this table like we did when we talked about this before. Okay, so we'll have the top here be the degree, and we'll have the side here be the leading coefficient. So if the leading coefficient, we look at that and we need to decide whether it is positive or whether it is negative. And then with the degree, we need to decide, is the degree even or is the degree odd? If you remember from before, when the degree is even, the arrows are going to go the same direction. So positive, they point up. Negative, they're going to point down. So even positive, the ends would go up, up. Even negative, the ends would go down, down. Now, odd, the arrows are always going to be opposite. And if you just remember, the plus or the minus tells you what the arrow on the right side does. It tells you what the last arrow does. And if you just remember its end behavior, it tells you about the end arrow. So if it's odd and positive, that means my last arrow goes up, so my first one has to go down. And if it's odd negative, that does the opposite. So odd negative, the last one goes down, so the first one starts up. And so you can look back in your notes from the beginning of chapter 4 on end behavior if you need to. But so that's the first thing we're going to look at, is what is the end behavior. Then we're going to figure out the zeros and their multiplicity. You might already have it in factored form. If it does, that's great. You can go straight to solving for your zeros. If it's not already factored, then we're going to have to do that. So that'll be what we do. And then step 3, if you wanted a really accurate graph, okay, so this third step here is for more accuracy. We're not actually going to focus on that right now, but if you wanted to get a more accurate graph, you would need to pick a few key x values to put in a table to plug in so you could figure out how high or how low to make your points. And if you look at the notes that I posted on the course calendar, I did go ahead and do that so you could see more specifically what the graphs come out to, but that's not something that we're going to really focus on today. So let me move this so that we can look at this example here. All right, so I want to find the zeros of this function, and then I want to sketch a reasonable graph. So the first thing that I'm going to do is determine the end behavior. So I need to determine what I have. It is in standard form, so that's the term I'm going to look at. And I see that I have a negative here and I have a fourth power. So that tells me that my leading coefficient is negative and my degree is even. So think about what that means for the graph. That means that our arrows, our end behavior is going to be down on the left and down on the right. Okay, so that is step one. Step two, we need to find the zeros. And so to do that, we take out the f of x and we put a 0 in there, so it's an equation that we can solve. So I'm going to say negative 2x to the fourth plus 16x squared minus 32 equals 0. And we're going to solve this equation. So we start with a GCF. Here's kind of an important point. And we've seen this more when we factor by grouping, not necessarily so much when we're factoring in general like this. Anytime your expression starts with a negative, your GCF has to be negative. So since our leading coefficient is negative 2, we need to factor out at least negative 1. So even if they had no other numbers in common, we would divide them all by negative 1 and factor that out. But here we can actually do more than 1. So we do have a GCF of negative 2. So I'm going to start by factoring that out. When I divide by negative 2, that's going to switch all my signs. So now I have positive x to the fourth minus 8x squared plus 16 equals 0. And this, if you verify, is in quadratic form. X to the fourth, that's an even power, and then half of 4 is 2. That matches my middle term, and it's got 3 terms altogether. So that's how I know it's quadratic form. And so I can set this up to factor just like we do any other quadratic. What multiplies to 16 and adds to negative 8, you can think about that for a sec. It's going to be negative 4 and negative 4. Since I got the same thing on both sides, hopefully you're starting to see that means I have a repeated root. So I'm going to have a squared factor there. Rather than writing it side by side, if they repeat, you need to write them using exponents. So I have negative 2 to the x squared minus 4 squared equals 0. And now x squared minus 4, that's a difference of squares. Now here's where this gets a little bit tricky. Since I'm squaring this, I have one factor that's squared. That means that any factors that come out of that are also going to be squared, because that x squared minus 4 actually happens twice, x squared minus 4 and x squared minus 4. So I'm going to get 2 matching sets of factors. So what we'll end up with is negative 2 times x plus 2 squared and times x minus 2 squared, because that was a difference of squares. That's kind of a unique one. A lot of times you won't see that, but that is something that you want to keep track of. So now we can solve this and get our zeros. I have x equals negative 2 for this one, and I have x equals positive 2 for this one. I don't get a solution from the GCF because there's no variable there. It's just negative 2. 0 can't equal negative 2. And so we have 2 solutions. Now what's important here is we need to know the multiplicity of each one. So again, you look at the factor that it came from, and they both came from squared factors. So this has a multiplicity of 2 and a multiplicity of 2. Now we have to decide, what does that mean? So 2's are both even, and even means that our graph is going to bounce at both of these points. Okay, so now we have everything that we need to know to be able to come up with a sketch of the graph. So I'm gonna just sketch something out here. You notice I didn't even put graph paper on here. So I'm gonna say that negative 2 is right here, and that's where one of my x-intercepts is. And positive 2 is right here. That's where I have another one. And so we're gonna kind of mentally think through what this is going to look like. I know, I'm gonna put this in highlighter, my arrows have to go down on either side. So that means I have to start from the bottom of my graph and come up towards the x-intercept. It's going to bounce off of both of those. So if I start on the left, my graph is going to come up until it gets to the -2. Then it has to bounce off right there because that's what the multiplicity told us. Well, now it has to head for the next x-intercept. So it's going to have to turn around and head to 2 where it bounces again. And because my arrow should end down, I know it's going to look something like that. Now, if we plugged in some points, like maybe we want to plug in 0 so we can see where along the y-axis we're supposed to get some points, we could do that. And then we could put a scale on it and we would get something a little bit more accurate. But this is just to get an idea of the shape. We just want to be able to see that it's got like 2 humps, basically, is what we're trying to see. So end behavior, figure out your arrows. That's really going to help you know how to start your graph. Then you factor and solve. That's exactly what we've been doing. That's not new. Once you get the solutions, you look back at the factors to determine the multiplicity, and that tells you whether to cross through the x-axis at that point or to turn around at that point. I'm going to do one more example. If you feel like you've got it, you can save this one to look at later if you want to, or just stick around to get this last little bit of notes. So, same process. Our first step, we're going to start by figuring out the end behavior. So, I have a leading coefficient of +1. So, it's positive. And my degree here is 3. So, it's odd. Odd positive means my second arrow goes up, so my first arrow has to go down. That's what our end behavior is going to look like. Now I need to factor and get my zeros. So I have x to the third plus x squared minus 6x equals 0. I have to put the 0 in so I have an equation that I can solve. I have a GCF of x. So I get x squared plus x minus 6 equals 0. And this one is already, it's a quadratic. So we're just going to factor that. What multiplies to -6 and adds to +1? I get 3 and -2. So I have, because this is a shortcut, a is equal to 1, x plus 3 and x minus 2 equals 0. So let's get our solutions. X is going to be 0, x is going to be -3, or x is going to be +2. Again, the 0 comes from this first one, because when does x equal 0? When x is 0. Now I need to decide what my multiplicity is for each of these. So in order to do that, I think my internet's being weird, so there's a little bit of a lag. Hopefully this doesn't look too bad on your screen when you're watching this. I have to look at the exponents of each of the factors. So 0 came from x to the first, so it has a multiplicity of 1. And actually all of them, I don't have any other exponents, so all of them have a multiplicity of 1. That means that at each of these values on the x-axis, the graph is going to cross. Odd multiplicities cross. And so we can set up a graph. You can probably hear my dogs coming in and out of their doggy door. I need 0, -3, and +2. So let's call this -3, let's call this +2, and obviously that's 0. So those are where my x-intercepts are, so I'm going to go ahead and put those points there. And now again, we look back at our end behavior. I know it has to start pointing down. So on this side of the graph, I'm going to start under the x-axis, come through it, then aim for my other one, and then aim for my other one. And I should end going up. So at each of these x-intercepts, it's going to cross. So I start down here because that's where my arrow is supposed to go. I'm going to head for the -3. Then I have to turn around and cross again, and then turn around and cross again. And so I see that this is going to be one of those kind of roller coaster looking curves. And that's really all there is to it. So you're just going to work on matching. And so that's all that we're going to look at for today. Be safe this weekend with the ice, you guys. I hope that you are really careful, and hopefully we'll be back at school on Tuesday, and I will get to see you then. Guys, have a great weekend.